Hello everyone, I hope you are doing well. In this video, we'll be talking about operators in quantum mechanics. So this is a requested video and we are gonna cover the basics of quantum mechanics. And first of all, I wanna mention the operators that we use in quantum mechanics. The basic operators. Actually, the basic operators are the ones on the basis of which the other operators are derived. Okay, and they are the basic ones. There is nothing below them. Okay, so let's first see what we mean by operator, because in quantum mechanics everything is related to operators. Every physical observable is expressed in terms of operator. Okay, whether it's energy, momentum, or position, or angular momentum, or whatever it is, we represent them by their corresponding operators in the equations that we consider. Okay, for example, the Schrodinger's equation involves the Hamiltonian operator. So yes, in quantum mechanics, every physical observable is expressed and calculated via the corresponding operators. So first of all, I want to mention the definition of operator, the general definition that will enable you to understand what operator by word means and how we represent a operator in general. Okay, and after that we'll be seeing some of the important operators in quantum mechanics, and in next video we'll be dealing with their application. So in general, an operator is represented by a hat over the symbol of physical observable whose operator, corresponding operator, is that. For example, let's say if we want to have a operator for position, we normally represent position by x in 1D and r in 3D. So these are the symbols for this physical observable, and if we want to have their corresponding operator, what we'll do is to put a hat over them. So that is the representation of their corresponding operator. Okay, that is what I wrote here. So let's say the physical observable is A, so we'll put A hat over there. An operator is a mathematical rule that when applied to a ket that we represent by this sign, we can use a word ket or you can use the word wave function. Both of them are equivalently correct, so you can use a ket word or wave function. They are equivalent, so you can use both of these words. So when a operator is applied on a ket or wave function, it transforms the wave function into another wave function, or you can say it transforms the ket into another ket. Okay, prime on it, which means that it has been changed. So that is it. That's the definition of ket. And when it's applied on a bra vector, it changes a bra vector from one to another form. So for example, it might be 1 previously and it can become 3 after the application of operator. Okay, so that means the value of operator might change. In some cases it doesn't change, but that's an exception. In general, an operator is something, it's actually a mathematical rule. It holds the mathematical form, and when it's applied on a wave function, it changes that wave function into another wave function, or it changes the ket to another ket. So that's the definition of operator. And yeah, now let's see what are the important operators in quantum mechanics that we'll be using everywhere in quantum mechanics. Let's first talk about the position operator, because it's the simplest operator that we have in quantum mechanics. And let's see what we use to represent position operator. So in one dimension, if you are considering the x dimension, then as I told you earlier, the rule to write the operator representation is that whatever observable you have, let's say we have x dimension for position, so you'll write the symbol for it, which is x, and put a hat over it. That is its operator representation. Similarly, if you are considering the y dimension for the position, then you'll have y and and a hat over it. That's its representation in terms of operator, and then we'll have z and a hat over it. It represents the x operator, that's the y operator, and that's the z operator. These are all position operators in one dimension separately. And if you're considering the three-dimensional case, then what we'll have is the r operator and a hat over it. We know in three dimension we represent position by r symbol, so we'll have a hat over it. In some cases we have theta. In other coordinates, for example, if it's spherical coordinates or cylindrical coordinates, it's theta with a hat over it, it's phi with a hat over it. Okay, it depends whatever the symbol you are using for the observable. Okay, it just links to the symbol you are using to represent that observable. If it's theta, then you'll use theta with a hat over it. If it's r, you'll use r with a hat over it. Okay, so that's the simplest representation for position operator, and we'll see the application of each of these operators in separate video because I don't want to mix all these things. In this video we'll be seeing the formulas and rules, the mathematical rules for the operator we are considering. In position operator there is no rule, that is it. Okay, it is not equal to anything else, that is it. There is one more thing that we can do in 3D case. In 3D case, in normal vector form, we know that r is equals to xi hat plus yj hat plus zk hat. That is how we link the three-dimensional case with the individual dimension cases. That's the x dimension part, that's the y dimension part, and that's the z dimension part. So we simply have a vector sum of them, and that is actually equals to the r vector. So what happens when we want to represent our operator in 3D in terms of their 1D parts? So it's simply this vector equation that we already know in classical mechanics, so we'll put hat over it and we get its 3D form. Okay, that is the position operator in 3D case, if you really want to consider its representation in 3D. Okay, and similarly it happens in dr differential form as well. So we'll have dr equals x dxi hat plus dy j hat plus dz k hat, and you can put the hats over them, maybe probably on like that or something like that. Okay, well, it's not compulsory to put hat on everything to show that it's our operator. We can see that we have multiple digits involved in here. We have dx, two digits, dy, d and z, and we are confused at where to put the hat on. So to avoid complications, we can do one thing, that we can put this whole thing to be equals to capital D, like instead of dr you can write capital D and a hat over it. Okay, so to show that it's a differential operator. And sometimes we don't need to do that as well, because these operators conveys their mathematical rule or formula shows that they are operators. So we don't need to put hat on everything, especially on those operators that involves a valid and clearly defined mathematical formula. So dx, dy and dz doesn't need a hat over them. That's something that I want to say, and you can ignore or avoid writing a hat over them. You'll see, for example, later on that in momentum operator we have momentum operator in x dimension to be equals to minus iota h square partial by partial x. Okay, we don't need to put hat on x, we don't need to do that. We just need to put it equals to p hat, px hat, to show that it's momentum in x dimension. Okay, and its operator, just put it equals to a variable and put a hat on it. So that's all we can do, and that's the point that I wanted to make here. I hope it's clear, and let's get back to the video. Now let's talk about the momentum operator, and you'll see the difference between momentum operator and the position operator and rest of all the operators from the position operator. That rest of all the operators had some mathematical rules associated with them that we can apply on the wave function, but in position operator that's not the case. It's simplest application you will see. So in momentum operator, if you are considering the momentum in x dimension, so it's a small p with x in subscript. Small p, it's small, okay, it's like small p with x in its subscript, small p with a y in its subscript for y dimension, small p with a z in its subscript for z dimension, okay, and a hat over it to show that it's their corresponding operator, okay. They assemble and then a hat over it to show their corresponding operator. So it's momentum in an x dimension operator, this is momentum in y dimension operator, this is the momentum in z dimension operator. Okay, whenever you want to differentiate momentum in a particular dimension from the others, then you use the subscript like x, and you just differentiate it from the other dimensions. Okay, so if you want to represent it in a general way without any differentiation, then you can use small p with a hat over it. Okay, it also shows the momentum in 3 dimension, or a general representation of momentum, which is simply p. Okay, so that is momentum in 1 dimension, that is momentum in general and in 3 dimension. So let's see what is px, py and pz, so that we can know their, that is simply their symbol. Now let's see what they equals to. In 1 dimension, we have small p x in subscript, hat over it, that is equals to minus iota h cut partial by partial x. Okay, that is px hat, momentum in x dimension. If you want to find out momentum in y dimension, it's y with a subscript y minus iota h cut, same, but partial by partial y here. Similarly for z, you must be guessing it right, it's partial by partial z over there. Okay, there is only difference of symbol or variable. Okay, so that is the momentum in x dimension, momentum in y dimension, and momentum in z dimension. Just like the position operator, you can see we can do the same thing for the momentum operator in 3D. So we have momentum operator in 3D to be this with a hat over it, that is equals to px I hat plus py j hat plus pz k hat. I hat, j hat and k hat are the unit vectors, so it will be a hat over px because it's operator representation. Okay, and what we can do here is to find out the value of the momentum operator over there. So we can put the value of px, py and pz here to see what it actually equals to. So we can put the value of px, which is minus iota h cut partial by partial x, I hat minus iota h cut partial by partial y, j hat minus iota h cut partial by partial z, k hat. Okay, further on what we can do is to take minus iota h cut as common. Okay, let's take it common and we'll write it outside, so we can do it here, taking minus iota h cut common. So we are left with partial by partial x, I hat plus partial by partial y, j hat plus partial by partial z, k hat inside. And if you recall, then this is actually the del operator, so we can write minus iota h cut del operator over here. So we can see that the momentum operator in 3D is actually equals to this in reduced form, in compact form. Okay, so that form is quite hectic and it requires us to put the values and all that stuff, but del operator is a operator that is frequently appearing in many formulas and operators in quantum mechanics, so that's a preferable form, but you should know what it equals to in terms of the components. Okay, so that is how we can generate, we have these basic formulas in 1D cases and we can get the 3D case. So it's actually, you can see minus iota h cut in 3D, you will replace this by partial r, which is del. Del is actually also equals to partial by partial r hat. Okay, in 3D, but we normally use this form. All right, so we have this situation now, and this is the momentum operator in 3D, this is the momentum operator in 1D cases. Okay, and I hope that is clear to you people. position operator in 1D, position operator in 3D, momentum operator in 1D, and momentum operator in 3D. You can see that momentum operator is equals to a mathematical rule. This is a mathematical rule. It is further equals to a mathematical rule that applies on a wave function, and we have that situation going on. But in position operator, they are just like that. They are not equal to anything else. That's basic. So momentum operator, now let's see what Hamiltonian operator is, which is also the energy operator. So that's the third and the last operator that we'll be considering in this video. We'll be talking about the derived operator, okay, like angular momentum operator. They're all derived from these basic operators, okay, like the angular momentum operator, L is equals to R operator cross P operator. Now let's talk about the Hamiltonian operator, which is also known as the energy operator because it gives us the energy of the system. Okay, that is the energy operator, and that is one of the most important operator in quantum mechanics. We use them frequently in all the systems that we consider because we are interested in knowing the energy of the system, momentum of the system, angular momentum of the system, and Hamiltonian or energy of the system. So these are the basic observables we are seeking in any quantum system we are studying. So knowing their operators is really important. So as we can see that it is the energy operator, so we use H hat. That is its representation. H means Hamiltonian, and a hat over it shows the operator of it. Sometimes we use E with a hat over it, but that's not common. H hat is common representation of energy operator. So that is represented by H hat, and that is equals to kinetic energy plus potential energy. That we already know that the energy of a system is equals to is kinetic energy plus potential energy. Now what is kinetic energy equals to and what is potential energy equals to? Potential energy is always sensitive to the case we are considering, but kinetic energy term could be written in terms of other things like momentum and all of this system. So H is equals to kinetic energy is actually equals to P square by 2m. P is the linear momentum plus potential energy we can represent it by V. Okay, so that is actually V, nothing else. That's simply V. Now that is the Hamiltonian operator in terms of linear momentum, and if we put the value of P in here, let's say in 3 dimensions, so what we get is minus h square by 2m delta square plus V. That is the Hamiltonian in 3 dimension because I put that one value. Let me do that. Okay, let me do that for you so that you are not confused. P in 3 dimension is equals to minus iota h cut delta, and if we put the square on it, so it's like that. Minus square becomes positive. Okay, iota square h cut square of them. Okay, del square by 2m, the same way because there is no square on 2m. Iota square is equals to minus 1 h cut square delta square by 2m plus V, and minus could be written the same way, so minus h cut square by 2m del square plus V. That is the Hamiltonian operator in 3D. Okay, and if you want Hamiltonian operator in 1D, it's simply like that. If in place of del square you'll use partial square by partial x square plus V. If you want to write it in Y form, so you'll simply write like that, and if you want it in Z, you'll replace Y by Z. Okay, that's really simple. If you're considering 3D, use del square. If you're using 1D, use partial square by partial x square. These things remains the same. Okay, so I'll say that this is the Hamiltonian in 1D. Okay, and this is Hamiltonian in 3D. All right, and this is also one of the general form for 1D, 2D, 3D or whatever. You can put x in here to show it's 1D, and you can use simply p to show it's 3D. Okay, and v could be a function of r and t, position and time. So that is it. I hope you got it. The formulas: 1D, that's the 3D. Okay, 1D, that's the 3D. Simply replace the partial derivatives with del operator to convert them into 3D case. This is the Hamiltonian operator in position space. You can see that it has the position variables in it. So we can have a Hamiltonian operator in time space as well. So for that purpose, in position space, we have h here to be equals to minus h square by 2m partial square by partial x square plus v of x and t. It could be a function of time as well. That is something that we are writing in general. But if you're considering the time independent case, then you can simply write for time independent case, we'll have simply h to be equals to minus h square by 2m partial square by partial x square plus v of x. Okay, this is in general because there could be a possibly any dependence, but in time independent case we have this situation. Okay, and in time space we can also have Hamiltonian operator in terms of time operator. So it is equals to iota h cut partial by partial t. Okay, so that is the Hamiltonian operator in time space, or you can say the time dependent operator. Okay, this is the time dependent Hamiltonian operator, and we can also write it as minus h cut by iota partial by partial t. We can prove it really simply, like if we have iota h cut partial by partial t, we can multiply iota both above and below. So in numerator it becomes iota square by iota h cut partial by partial t. Iota square is actually minus 1, so it's minus h cut by iota partial by partial t. So you can convert it from this form to another form by doing this thing. So that is the time dependent Hamiltonian operator, and this one is the position dependent Hamiltonian operator. Okay, so this is also position dependent Hamiltonian operator. These are the general cases. That is the specific case in which the potential is independent of time. So that is the special case, and these are the general cases. I'll be taking out the general cases first, and then we'll convert them into the special cases of time independent cases, because mostly we'll see later on that we have the time independent Schrodinger equation, and we'll be using it later on. But for now I was just considering that we should consider the bases in general terms, and then we can reduce them into specific terms. So we can see the formula of Hamiltonian in position space, and this is in time space. And if we apply psi on both sides, what will happen? This is psi, psi, and psi. And here we'll apply psi, we'll write it on the right hand side. Okay, since both of them are Hamiltonian operator, applied on psi, since their left hand side is equal, their right hand sides will be equal to each other. So we can put this to be equals to this. In this way we can get the time dependent Schrodinger's equation, and from time dependent Schrodinger's equation you can get the time independent Schrodinger's equation. Both of them are connected to each other, so we can put both of these equations equal to each other. Minus h square by 2m partial square by partial x square plus v of x and t, that is equals to iota h cut partial by partial t psi. Okay, or you can see that this is the Schrodinger's equation. This is this one specifically, and also this one, time dependent Schrodinger's equation. Because we can see that it is dependent upon time and it's sensitive to time. Oh, I didn't write psi over there, so they should have psi in there. Okay, because it applies on psi. So this is the time dependent Schrodinger's equation. Now let's see how we can convert it into time independent Schrodinger's equation. Okay, because time dependent form is the basic form and we can extract the time independent form out of it. So what's the basic thing is the time dependent equation. So we have the following time dependent Schrodinger's equation that we derived right now. It is minus h square by 2m partial square by partial x square psi, okay, which is a function of x and t, okay, because that is something that we are writing in general. So v is a function of x and t, then we have psi, which is function of x and t. That is something that you will be practicing and doing multiple times later on, so practice it. Partial by partial t of psi x and t. Now let that psi x of t is separable, then we have psi x of t to be equals to psi of x and psi of t. Separable means that the time dependent part and the position dependent part could be separated into two functions. Okay, so we have psi x of t to be equals to psi of x and psi of t. It happens in some cases, in some wave functions, that we can simply and completely separate the position part from its time part. Okay, so that it's simply the position component, all the position terms in one place and all of the time terms in one place, and nothing is mixed. Okay, we can separate them. So that is what we are saying here. So let's psi is a separable wave function and it could be written like that, and let potential is position dependent only, it doesn't depend upon time. Independent of time. So these are the two assumptions that we make while deriving the time independent Schrodinger's equation. These are the two assumptions. The first is that the wave function is separable, and the second is that the potential is position dependent only, it doesn't depend upon time. Okay, so we have v of xt to be simply equals to v of x. So these are the two substitutions that we'll make in this equation. Let it is equation number 3. So let's put them in here. We have psi of x, psi of t, plus we'll have v of x, psi of x, and psi of t, iota h cut partial by partial t on psi of x and psi of t. Okay, and you can see that partial square by partial x square, it involves only x variable, doesn't contain t, so we can take psi of t out of this operator. We can write it right here separately. Okay, and we have minus h square by 2m into partial square by partial x square psi of x. The operator only applies on the position part, so we can take the psi of t outside of it. Similarly, we can take psi of t separate and we have v of x, psi of x simply. You'll see why I'm doing it. Okay, and here we can see it's partial by partial t. It's a time operator, it will only be applied on time variables. So psi of x only contains x variables, so we can take it simply outside. So it's psi of x partial by partial t on psi of t. Now we can take psi of t common here. What I am doing is to make one side x dependent and the other side time dependent. Okay, we are separating them completely. So psi of t is taken common, so it's minus h square by 2m partial square by partial x square psi of x plus v of x psi of x, that is equals to, we can take psi x common here, so we have iota h cut partial by partial t psi of t. Now I'm taking this psi of x into this side, it's multiplied here, it will be divided here, psi of t being multiplied here, divided there. So we have 1 over psi of x minus h square by 2m partial square by partial x square psi of x plus v of x psi of x and 1 over psi of t iota h cut partial by partial t psi of t. Now you can see that this side is completely x dependent and this side is completely time dependent, and time and position dependence are linearly independent of each other. So there is no way this situation holds until unless they are equals to a constant value, which is the eigenvalue of the Hamiltonian operator. So they both should separately equals to the energy of the system, the energy corresponding to the psi wave function. So we'll put them separately equals to a common constant, common eigenvalue E, okay, as both sides are linearly independent, so they don't affect each other, they don't affect each other's values, so they will separately be equals to a common constant. Let's say it's E and it's E, and it's the only way this equation holds. Okay, if this is equals to E1 and this is equals to E2, then E1 is not equals to E2 and the situation will not satisfy, because it's E1 in here that should be equals to E2 in here, and that's only possible if E1 is equals to E2. I hope you're getting my point, that whatever they are equals to, they should be equals to the same thing on both sides, because that is something this equation demands. It's equation, it's equality of this term with this term, so they should be equals to a same thing, which is the energy of the system. Okay, so we'll put this to be equals to E and this to be equals to E. I'm considering this part only because that is something that will give us the time independent Schrodinger's equation. So we'll put them separately. Let's first derive the time independent Schrodinger's equation, and that should be equals to E. Okay, and we can take this to the other side, so we have this situation. To psi of x, this is the time independent Schrodinger's equation. Okay, this is the time independent Schrodinger's equation, and we can see that it's really simple, and it normally what it involves is that we can write it in 3D, as we'll replace this derivative with del operator plus v of x, and we can take psi of x as common. Okay, so it's psi of x here, e into psi of x. This is actually the Hamiltonian operator, so we can write Hamiltonian operator over there, then psi of x equals e times psi of x. This is the eigenvalue equation where e is constant and e is the eigenvalue of Hamiltonian operator that gives the energy for the system whose wave function is psi. Okay, so you can see here that what is it all about. Okay, and if we consider this side, we had 1 over psi of t, that is iota h cut multiplied by iota h cut partial by partial t psi of t, and that should be equals to e as well. Okay, and we can take psi of t to the other side, so it's iota h cut partial by partial t psi of t e times psi of t. Okay, this is what we got, and we can use the separation of variable technique to solve this differential equation. So this is partial of psi of t, and then we have partial t in the denominator, iota h cut, it's a whole constant term, and then psi of t. We can take psi of t here, and we have psi of t here, okay, in the denominator, and we can take psi t here, so like that. Okay, and I don't know if you know how to integrate. So this is what we got. we can integrate both sides now. This is constant, so integration only applies here. So integration of 1 over psi of t when the differential contains this term, it's just like we have 1 over x dx. Okay, this is just like that. Here x is psi of t. Here you can compare the situation, and its integration is natural log of x simply. Okay, so the integration of this term is natural log of psi of t. Sometimes this situation happens and you have to simplify it, so that is why I'm doing it. E by iota h cut. Integration of partial t is simply t multiplied or adding some constant side by side, which is, let's say, a1, which is the integration constant. And instead of a1, I'm wishing to write natural log of a1 because it's natural log in here, so I want a particular term to be formed, so that is why I'm using natural log of a1 instead here, because it's a constant. I can write even anything, exponential a1 or whatever I want, so natural log of a1 works fine for us. So that is it. This is what we got so far. We want psi of t, so for that purpose I wanna do one more thing. Okay, here I'm gonna write natural log of e, because natural log of e is equals to 1 and 1 is everywhere, so I can write it. And it's the property of logarithms that anything that is the coefficient will appear on the power of this thing. So natural log of e to the power et by iota h cut plus natural log of a1. And it's the property of logarithms again that if there are two logarithms being added, we can write it in a single logarithm and the two terms being multiplied. So it's a1 times e to the power et by iota h cut. Okay, and it's natural log of psi of t here. So natural log cancels out, and we have this situation: psi of t to be equals to a1 e to the power et by iota h cut. Okay, and 1 over iota, you know, that is equals to minus iota. You can do this multiplying iota above and below. Okay, and it's iota over there, and this is minus 1, so minus 1 becomes minus iota, so you can write it equals to a1 e to the power minus iota e t by h cut. Okay, that is the time dependent wave function, and this form frequently appears, and that is why I derived it for you people, so that you may know that how it originates, besides the time independent Schrodinger's equation, which is position dependent. So this is the wave function that we got for the time dependent part. Okay, and we will see in later in some problems, so that is why I derived it. You should know it. Okay, so we can summarize this whole video. Here we can see the position operators. Okay, x operator, y operator, z operator, r operator. In 3D we can write it like that: momentum operator, x, y and z representation. And then in 3D we saw that it is equals to this, where del is equals to this. Okay, in Hamiltonian operator we saw that it is equals to this term. Okay, we can put hat over the potential energy term as well, because it's operator basically. So in 3D we have this situation. This is the 1D case where we use the x dimension only, partial square by partial x square. In 3D we use the del operator form, or you can use the p form as well. So it's actually equals to kinetic energy term plus the potential energy term. This is the kinetic energy term. We have p square, where p is the momentum operator. So in 3D we can put the momentum operator in 3D part. Okay, and doing so it becomes minus h square by 2m del square plus v, and that is it. This is the Hamiltonian operator in 1D. This is the Hamiltonian operator in 3D. Moving on, using the Hamiltonian, we saw that this is the Schrodinger's equation. Okay, we wrote the position dependent form. Let me write the time dependent form, which was iota h cut partial by partial t. Since we can see that both of these are Hamiltonian, so they must be equal to each other. Okay, so that is what we did here. We also used wave function. We applied the wave function on the right hand side. Okay, so additionally we wrote the wave function here. So this is the time dependent form, and we can write it like that. In place of h in here, we can write the position dependent formula in here. I use the 1D forms. You can use del square in place of, you know, this thing to convert it into a 3D case. Okay, that's really simple. Just use r in place of x in there here, and in here you can use del square. Simply for time case you don't need to change anything, and that is the time dependent form Schrodinger's equation. That is the time dependent form of Schrodinger's equation. You should know it because it's the basic one, and using some assumption we can derive the time independent form, and we derived it. You saw that we got this form, and in H we have the potential energy term that is independent of time. There is no time involved in here, we can see in the whole equation. So this is the time independent form. You can easily remember it from this equation. Okay, you just need to remember what is age equals to. Age is equals to this. You just have to remove the time t here, and rest of everything is the same. Okay, you can easily remember this form because it's really important. I think that much detail is enough for this video, and we'll be seeing the application of all these operators and these forms in later videos. And if you have any queries, if you want me to add more details into this video, let me know. I'll do that. And till then, take care and goodbye. Here, besides the all these details, we can write the time dependent wave function as well, minus iota e t by h gut.